Here we are with our first group of examples for Module 5.2. Coming out of Module 5.1, recall that Module 5.1 introduced us to exponential functions. And now in 5.2, we turn and take a look at logarithmic functions related to exponential functions and needed in order to work with exponential functions and in particular solve exponential equations. The way I like to think about logarithms to help students kind of grasp what's going on here, because a lot of students find logarithms to be a bit challenging. I get that, but they don't have to be. If you understand what a logarithm is, what we mean when we talk about logarithms, then it's really not too bad. And it starts with the definition of a logarithm here from your textbook, from your pre-class notes. The definition of a logarithm is that y equals logarithm base b of x is the same thing as saying b base b to the power y equals x. The connection that I make, or not, connection's not exactly the right word, but the analogy that I make is something that you guys are already familiar with. Let me write it here, as this is analogous to something that you guys already know. You know the cube root of 8 equals, you should be able to fill in the blank here, 2, because you know that 2 to the third power equals 8. This is not logarithms. I'm not talking about logarithms here. I'm saying it's analogous to the relationship between powers and radicals. You know the cube root of 8 equals 2 because 2 cubed equals 8. In a sense, the cube root of 8 equals 2 and 2 cubed equals 8 are saying the same thing. They're two different forms of the same information. If 2 to the third power is 8, that's really the same thing as saying the cube root of 8 is 2. Logarithms and exponentials are the same way. Logarithms and exponentials are two different sides to the same coin, just like powers and radicals are two different sides of the same coin. And you already know in your work with powers and radicals that radicals are useful, even though they're not perhaps your favorite to work with. Radicals, they're useful because radicals are the opposite of powers and they cancel powers and they help you solve. A very, very similar and analogous kind of thought process goes into the relationship between exponentials and logarithms. And we'll use these first 4 examples to start that conversation, that a logarithm is the opposite. It's in some way equivalent to, it's the same information as an exponential, but it's the opposite form of an exponential. In mathematics, we use the term inverse. It's the inverse form of an exponential. And because it's the inverse, then logarithms and exponentials, as we will learn over the next couple of modules, they cancel each other out, just like radicals and powers cancel. And that's a useful property, because when we're solving, we need to cancel so that we can solve for the variable. So logarithms and exponentials are inverses. They'll cancel each other out. That's the usefulness of logarithms. And that's something that we're going to get to in module 6, yes, in module 6, 6.2 in particular. So a little bit later on, but I want to kind of set the stage for that right now. For now, and for this set of examples in particular, let's just make sure that we see how to rewrite exponentials and logarithms in equivalent forms. And you'll note here that I have that I'm working questions 3 and 4 from your class notes first. I think it's easier to start with something we know and work toward something we're less familiar with. Like in example 3 here, I've got 3 squared equals 9, and I want to rewrite that in exponential, it's in exponential form. I want to rewrite that in logarithmic form. And an exponential always has a couple different colors here. An exponential always has a base that we'll typically call b, a power. In this definition, we use the letter y for the power, and a result. So we've got let me write that out, a base to a power equals a result. So base to a power equals a result. You're going to use all of that same information in logarithmic form. You've got log, let me write it out in same colors here. I've got a power, the power y equals log base b, so the subscript on the logarithm is my base, and then in the parentheses here I have my result x. What's happening here is we're kind of shuffling things around, just like in the little analogous radicals and powers. We're shuffling the numbers around and turning it and converting it between radical form and power form. The same thing is happening here. We just have to get used to that transformation, get used to that transition. We're pretty comfortable talking about a base to a power and getting some result there. We're going to flip that coin and say we can rewrite it in logarithmic form. Log of some base b of a result gives you the power as what that logarithm is equal to. In fact, I like to write it that way here. In English, maybe I won't say plain English, but in English, a logarithm is a power. All of these pieces of information we're going to come back to over and over again. The transforming between log form and exponential form, and what I've written here in quotes, a logarithm is a power, is something that's going to help us understand how to manipulate logarithms considerably easier than just trying to slog through the definition, and understanding that, oh, a logarithm is a power will help us out here. And let's start with these examples. If I have a base 3 to a power 2 is equal to a result of 9 in question 3, then I can rewrite that as log base is 3, of, in parentheses, the result 9, is equal to the power 2. So log base 3 of 9 equals 2. Just using that definition, and that's all we're doing here. Just using that definition to rewrite this exponential form to logarithmic form. Let's do the same thing with 2 to the negative 1 equals 1/2. That's true. 2 to the negative 1 power is equal to 1/2. We're going to rewrite that in logarithmic form as log base 2 of the result 1/2 is equal to the power -1. Now let's go back the other way. And in questions 1 and 2, use the same idea to translate log base 5 of 25 equals 2 into exponential form. Log base 5 of a result of 25 is equal to a power of 2. That might look more familiar if you think a base 5 with a power of 2 gives you a result of 25. And that's exactly what we get in applying this definition of a logarithm. And in question 2, we've got log of 1,000,000 equals 6. Now, this doesn't show a base, but you have to have read and understand that if you just have the word logarithm, then it is implied that you're looking at a base 10. So log means log base 10. So we have log base 10 of 1,000,000 equals 6. Log with a base 10 and a result of 1,000,000 is equal to a power of 6. 10, base 10 to the 6th power gives you a result of 1,000,000. There's the same fact in exponential form. We'll play with logarithms, logarithmic form, and exponential form a lot more in upcoming examples in 5.2.